Okay, next up I'm dealing with the Lewis structure for BrO2-. I would like to indicate the formal charges on my bromines and oxygen atoms, and then answer the following questions, indicate my number of valence electrons. So let's just write that out. So first, I would like my Lewis structure with my formal charges indicated. The second part, I would like to indicate the number of valence electrons. For the third part, I would like to know my preferred Lewis structure. D, how many resonance structures do I have? So we'll talk about this a little bit. And E, what is the shape of my ion? The name of my ion too. So this will relate to Vesper theory. Let's just do that super duper quickly. The way that this question is ordered, I'm going to answer B and C. Answering B and C will give me the answer of A. And so I need to count my valence electrons, as I said. So bromine is going to give me, let's try it out a little bit better. So I have bromine, I have O2, and I have a minus. So remember, minus charges mean that, so a neutral charge would mean that my number of protons equals my number of electrons, and the two cancel perfectly, yielding a net charge of 0. But a minus charge means that I have an extra electron compared to the number of protons that I have. So it means when I'm counting the valence electrons, I'm going to need to add that extra electron, which is why I need to keep note of the charge. So bromine gives me 7 valence electrons for every bromine atom. Oxygen gives me 6 valence electrons for every oxygen atom. And the charge is going to give me 1 valence electron per negative charge. And so that is going to give me 7 plus 12 plus 1. And that's 20 electrons to organize. Okay. Now I need to decide on my central atom. I can already see I have 1 bromine, 2 oxygens. It doesn't make sense for oxygen to be my central atom. It makes more sense for bromine to be my central atom, as there's more symmetry in that, and chemistry loves symmetry. So let's go ahead and put bromine right in the middle, and I'll put 1 bond to each oxygen. We can fill in everybody's octet and see what will be left over. Okay, so with this configuration, I have 6 by 2 on lone pairs on each of the oxygens, plus 4 lone pairs on my bromine, plus 4 in the 2 bonds. And so that's going to give me 8 plus 12, which is indeed 20 electrons. So yes, my 20 valence electrons have been taken care of, but this is where the formal charge becomes very, very important. As I said in the previous question, Lewis structures provide a method of electron bookkeeping, which is very, very important in quick determination of what the structure should look like. If it has a valid Lewis structure, the molecule should exist. And so even though it's completely empirically based with no basis in what is happening down on the level of quantum theory, it works very, very well for doing things quickly when you need to figure out whether something is plausible. And so let's check our formal charges. And I know that I'd need to minimize my formal charges and minimize charge separation if I want this to be a low energy molecule. And typically when you're asked for the Lewis structure, you want the lowest energy. And so for each of my oxygens, I have 6 valence electrons minus the 6 lone pairs minus the 1 they have each contributed to a bond. So this gives me a total charge of negative on both of them. And on my bromine, I have 7 valence electrons minus the 4 in lone pairs minus the 2 in bonding pairs, and that is going to give me positive 1. So I'm going to have 1 positive. And so, yes, I see that the net is correct. I have a net of -1, but my charge separation is not optimal in this case. I can minimize the charge on 2 of these and just leave a minus on 1 of them. That makes the most sense, and that would be energetically favorable. And so instead of having this, I'm going to move around some electrons and try and minimize the formal charge just a little bit more. So I know oxygen likes to have 2 bonds and bromine likes to have 1. So let's give one of the oxygens the 2 bonds and take away a lone pair on the bromine. That will leave me with that. Now I have 2, 4, 6, 8, 10, 12, 14, 16, 18. So I still have 2 more electrons. Let's just put them back on the bromine. Okay, and so now that I have this, again, let's count our formal charges. We'll call this oxygen 1 and oxygen 2. On oxygen 1, I have 6 valence electrons minus the 4 in lone pairs minus the 1, 2, 2 in bonding pairs. And so that's going to give me a net formal charge of 0. On the bromine, I have 7 valence electrons minus the 4 in lone pairs minus the 3 in bonding pairs, giving me 0. So great, I've minimized the charge on 2 of them. And on oxygen 2, I'm going to have 7 minus 6. Sorry, 6. My apologies. I have 6 valence electrons minus the 6 in lone pairs minus the 1 it has in this bonding pair. And that's going to give me -1. And so that is what I'm going to be left with. Now I've minimized the formal charges and the charge separation, which is great, and I have the net formal charge adding up to what I want it to add up to. And so I can come back up here and answer some of these questions. We found I have 20 valence electrons. Okay, now next up we need to discuss this concept of resonance structure. So now that I have my valid Lewis structure, resonance structures are any other valid Lewis structures. And why this is important is, so Lewis structures assume that that electrons are either localized in lone pairs or bonding pairs. We know from quantum theory that that is not true. Electrons can go wherever they want as long as it is energetically permitted by Schrödinger's equation. And so we need to factor that into what we have, and we can do that by writing down resonance structures that help delocalize these electrons. Why delocalization is preferred is because when electrons are delocalized, it minimizes their interaction with each other, and that minimizes the charge. Delocalization is good for minimizing the charge, and we always want to, not minimizing the charge, for minimizing electron-electron interactions, and we always want to do that because that will minimize the energy of our molecule. And so, are there any other ways that I can place the electrons and have a different Lewis structure, but that is permitted? And so, I can see that rather than having the 2 bonding pairs here, I can move one bonding pair back to the oxygen, right? Move this bonding pair onto bromine, and move one of these lone pairs onto this. And so just so you know, a double-headed arrow means I am moving both electrons. It is heterolytic. And a single arrow means that I am moving 1 electron, which is homolytic. And so when I do this, I'll end up with a second structure, which looks basically like this reflected in a mirror. And so they're not separate structures, they're the same wave function when you actually think about it, but with electrons arranged in a different way, which factors in that delocalization of electrons. And so now, instead I have this, the number of my electrons has not changed, and so I still have my 20, and now the minus charge is going to be here instead. And so I can come back up here and say that I have 2 resonance structures. Okay, now I need to, so these are the 2 preferred Lewis structures, equally preferred because you see the symmetry in it, so none has a higher weighting on the wave function than the other. And so now we figure out the shape of the ion. And so I need to go to Vesper theory. I need to figure out how many terminal groups I have on my central atom. And so for both bromines, I have 2 lone pairs acting as groups, and I have 2 oxygens acting as groups. And so I have 4 groups, and for its notation it will be AX2, E2. So 2 bonding pairs, 2 lone pairs. And so now when I come to my Vesper chart, I can quickly tell that the electron geometry, it won't account for which ones are lone pairs, which ones are bonding pairs, so I just go straight to a steric number of 4, and my electron geometry is going to be tetrahedral. For my molecular geometry, I now account for which ones are lone pairs, which ones are bonding pairs, and I'll find that this is actually going to be a bent shape. So I just come to 4, and I go right to 2 lone pairs, so that is bent. And so now when I draw it out, you can draw it both, or you can use the broken lines to show that the bonds are delocalized, depending on what your instructor would like. And so we're just going to draw both. So I have Br, oxygen, oxygen, and then I have my 2 lone pairs. Okay, and don't forget your minus charge. So those will be my 2 Vespers, right? Just one moment. Okay, so now that I have that, I'm going to scroll right back up. So the shape of the ion is going to be bent. And lastly, we need to figure out the name of the ion. So for my central atom, it's bromine. And I have I have 2 of them with 1 minus charge. And so this is di for the 2, ox for the oxygen, and ide to factor in that one of them is an ion. And so this would form bromine dioxide would be the name. And that's going to be it for this question. Okay.